So 3.2, we're going to learn about logarithmic functions. So the logarithmic function is the inverse of an exponential function. We can take something that's written in logarithmic form like this and put it into exponential form like this. So one way that I think about it, which the last class said that they liked some other ways better, if you have log base a of x, so y equals log base a of x, you take the base, that stays in the middle, I move the x over here to the other side of the equal sign, and then the y becomes your exponent there.
Wait, what was the other word?
They said that if you go from exponential form to logarithmic form, that they explained it as BAE, so like B-A-E. So you would have log, your base, then the answer, then the exponent. So base, answer, exponent. I can't write sideways. There we go. Base, answer, exponent. But that's if you go from exponential form to logarithmic form. I think the way that Miss Meadows does it is if you had log base a of x is equal to y, write the base, the x goes over there and the y goes up top, like this. So different ways to think about it. I would just kind of stick with one and do whatever makes sense in your head, because the more you practice it, the more you get used to it, the easier it'll become. But just stick with one way and work with that. So we can take something in logarithmic form, so that's when it has the word log, and put it into exponential form. So exponential form has an exponent. Here it gave us an example done. So 2 is your base, the exponent is your answer, and then the answer is the big number there, which on the next slide we'll do some more examples. So here, if I have 4 is equal to log base 2 of x, I would take my base, keep it in the middle, move my x over there, move my 4 to become my exponent. So I just took it from logarithmic form, put it in exponential form. Just switching them. So looking at b, what would my base be? 3. What's my exponent? X. And then what's it equal to? 9. Another way you can think about it is that here it kind of looks like 3 to the power of 9. It'll never be 3 to the power of 9. Here it looks like 2 to the power of x. It'll never be 2 to the power of x. You have to move that. It's not going to be that easy.
Are you just thinking like...
All right, so for a, here we're writing it in logarithmic form. So I always like to just write the one that's equal on the left. That's just me. But you can do it however, so I'm just rewriting it. I'm going to have log base what? B of what would come next? 16 is equal to 4. So I just flipped.
Where'd you get log from?
I'm putting it into logarithmic form. So the next one, I would have log base what? 5 of x is equal to 2. So here we're evaluating. So evaluate the function at the indicated value of x without using a calculator. So we want to plug in 64 into x. So this would be log base 4 of 64. And I'm just going to say that it's equal to y. So equal to y. Now, we don't know how to compute logs in our head yet, but we do know how to compute exponents. So I'm going to put this into exponential form. So what's my base? 4. What's my exponent? Y. And then that's equal to 64. So 4 to what power gives me 64? 3. So y would be 3. So your answer here is 3. For B, I'm going to take 1 over 6, plug it in. So I have log base 36 of 1 over 6 is equal to y. What's my base? 36. What's my exponent? Exponent. Y. And then it's equal to 1/6. So 36 to what power gives me 1 over 6?
1/2.
-1/2 would just be 6, but how does it equal 1 over 6? What's needed? Negative. So y would be -1/2. So when you're going to a smaller number, it has to be a fraction, because remember, if you had 36 to the 1/2 power, that's the same thing as saying the square root of 36, which is 6. So that's where we get that 1/2 from. And the negative is what turns it into a fraction. Next, we're going to be evaluating logs using a calculator. So our calculator only does one type of log, and that's the common log. So that is log base 10. So your calculator only evaluates log functions with the base of 10, unless you have a super new calculator that you can change the base, which not a lot of people have that. But there is a formula that you can put it in the calculator, which we're not going to do yet. We're just going to work with log base 10 for now. So your calculator only does log base 10. All right, so here we have log base 10, so we can put this into our calculator. So we have -3 log base 10 of 2.7. So in your calculator, you would do log of 2.7 and then multiply this times -3. What do you get?
I'm not even going to say my answer because I have to do it right.
-1.29.
Nope.
Michael, are you right?
Nope. I don't know how to use these calculators.
All right, next we have our properties of logs. So anytime you take the log, doesn't matter what the base is of 1, your answer is 0. So if I had log base 10, which you guys can do in your calculator, of 1, so take the log of 1, what do you get? 0. If I had log base 27 of 1, you would get 0. So it doesn't matter what your base is. Anytime you take the log of 1, you get 0. And the reason is because whatever that base is, so let's say it was 27 to the power of 0, that would be 1. For the next one, anytime you have log base a of a, your answer is 1. And that's because this should be an exponent here, not a subscript. That's because a to the power of 1 is equal to a. So a in these properties are just like an arbitrary number. It works for anything. So if I had log base 10 of 10, so in your calculator, if you did log of 10, you would get 1. Similarly, if you did log base a of a to the power of x, this log base a of a is 1, so it kind of cancels out, and then you're just left with x. So if I had log base 2 of 2 to the power of 10, log base 2 of 2 cancels, so your answer would be 10. Then we will try to make them the same. I'll show you in the next example, on the next slide. If you can't make them the same, then usually you just use your calculator to solve. also if you have log base a of x and that's equal to log base a of y, the log base a's cancel, so then you would just be left with x is equal to y. So this would work in examples where you had like log base 2 of x plus 4 is equal to log base 2 of 12. To solve for x, you would just say x plus 4 is equal to 12, because the log base 2's will cancel. And then you just set the rest of it equal to each other. All right, we're doing same properties here. So 3 to the power of log base 3 of 15.
The log and 3 is
The 3 and log base 3 cancels, so then what's our answer?
15.
15. B is the same thing. The log base 2 of 2 cancels, so then what's our answer? 3.
Is it gonna be this easy?
No.
No, look at D.
So for C, log base 9 of 9 cancels, so then what are you left with? 1. Because technically this is a 9 to the power of 1. So 1. D is kind of like the one we did on the last page. So how can I get 1/3 to be 3 to some exponent? -1. So I'm just going to change this 1/3 to log base 3 of 3 to the power of -1. So log base 3 of 3 cancels, and my answer is -1. So graphs of our logarithmic functions are inverses of our exponential function. So here this blue graph looks like the graphs that we did yesterday. This is our exponential function, so if we had 2 to the power of x. The pink graph here is log base 2 of x, and it's the inverse of it. So when things are inverses of each other, we know from like chapter 2 that we just take the x and make it a y, and take the y's and make it your x. So we're just flipping the x and y values here. Yes. So we're pretty much flipping our exponential graph to get our logarithmic graph, but our characteristics of our exponential graph also flip with it. So before, in this blue graph, our y-intercept was 0, 1. Next, we have an x-intercept here that's 1, 0, and there is no y-intercept. So just like we had no x-intercept in exponential functions, here we have no y-intercept. Yes, unless you have a shift. So if it shifts it, then you may cross the y-axis. So this is just for your basic functions when you just have like log of some number, log base some number of x. If you had a transformation applying to it, these characteristics get shifted around a little bit.
How do you show shifts?
It's on the next slide. You'll see. So then next, we have our y-axis as our vertical asymptote. So just like yesterday where we had a horizontal asymptote, we flip it and now it's a vertical asymptote, and that is x is equal to 0. So the domain of a logarithmic function. The log function reverses the domain and range of the exponential function. So before our domain was all real numbers, now our range is all real numbers. And then before our range was from 0 to infinity, now our domain is all positive numbers from 0 to infinity. But if we have a horizontal shift, our domain shifts with it. So if my graph of my log function looked like this, if I shifted it to the left, let's say 5 over here, that also shifts my domain to the left 5. So instead of being from 0 to infinity here, I shifted it to the left 5, so now it would be negative 5 to infinity. So your domain shifts when you have a horizontal shift. So if you shift it sideways. To find your vertical asymptote, you can set what's in the parentheses equal to 0. So if I had a function that was log base 6 of x minus 4, in the parentheses it means what's in here. So I would set that equal to 0. X minus 4 equals 0. X is equal to 4, so that would be my vertical asymptote. So again, your vertical asymptote shifts as your graph shifts sideways. And then you can always find your x-intercept by plugging in 0 for y. Same way we found our x-intercept in all of our other functions. So x-intercept, plug in 0 for y. If you notice, the transformations here are the same as the transformations for our exponential functions. If you add on the outside, you're moving up. If you subtract on the outside, you're going down. If you add on the inside, you're going left. If you subtract on the inside, you're going right. If you multiply by a negative, you have a reflection on the x-axis. So that's when the negative's on the outside, it's the x-axis. If the negative's on the inside, it's the y-axis. The way I always remember the difference is that you want to keep your x's outside your house. So if it's a negative, outside, it's the x-axis. I don't know, it's just the way I think about it. If you multiply by a number outside, you have a vertical stretch if that number is greater than 1. You have a vertical shrink if it's in between 0 and 1. And then if the number is inside, it's a horizontal shrink if the number is greater than 1, and it's a horizontal stretch if it's in between 0 and 1. So same functions as your exponential. Same transformations as your exponential function. All right, so here we want to graph our exponential function, which is 3 to the power of x, and our logarithmic function, so log base 3 of x. So we know these are inverses of each other. So I'm going to start by graphing our exponential because we know how to graph that from yesterday. So what are 3 numbers that I could plug in? -1, 0, and 1. I'm also just going to plug in 2 for fun. So these are my x's. I'm going to get values for y. So when I plug in -1, what's 3 to the power of -1? 1/3. What's 3 to the power of 0? 1. What's 1 to the power of 3? 3. And 3 to the power of 2? 9. So my points here would be -1, 1/3. 0, 1, 1, 3, and 2, 9. So I'm going to have a point here, 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 and here, off the graph, just for fun. So that is my graph of 3 to the power of x.
With that line, the horizontal asymptote would be 0
Mm-hmm.
and no vertical.
Right. Now to graph my log function, I want to flip my x's and make them my y's, and my y's are going to become my x's. So my points flip. So instead of -1/3, I have 1/3 -1. So I'm going to go to the right 1/3 down to -1. This one becomes 1, 0. So I'm going to go to the right 1, stay on 0. This one becomes 3, 1. So I go to the right 3, up 1. And this one becomes 9, 2. So I go to the right 9, up 2. And then that's my graph. So in my pink graph now, my log graph, what's my domain? 0 to infinity. What's my range? All real numbers. What is my x-intercept?
0, 1, or 1, 0.
1, 0. What's my y-intercept?
None.
I don't have any, so none. What's my vertical asymptote?
0,
X equals 0. What's my horizontal asymptote?
0.
There is none.
Are you always gonna ask for the log?
Alright, so looking at example 8. So I have log base 3. So I know this is going to be derived from the same graph that I had on that last page, the pink one, which I had a point at -1, 1/3, 1, 0, 3, 1, and 9, 2. So I just copied this graph from the last page. So my base graph is log base 3 of x. From here, I'm just going to apply my transformations to it. So what does this negative do to my graph?
Reflection on the x.
Reflection on the x-axis. So my x-axis is this one here. I'm going to treat that as my mirror. So whatever's on top is going to now be below. Whatever's below goes on top. So this point on it stays the same. My point below just now goes above there. My point above just goes below, and then that other point above goes below. So I just mirrored it along that x-axis. And then it looks like that. I have another transformation that is this -1. So what does that x minus 1 do to our graph? To the right. It moves it to the right one. So all of my points now for the blue graph, I'm going to go to the right one. So just move it to the right one, to the right one, to the right one, and to the right one. So my graph looks like this. Just be careful when you shift it to the right one, because my vertical asymptote was at 0. But I'm shifting that vertical asymptote to the right one. So now that x is equal to 1 is that line that my graph cannot cross. So make sure your graph doesn't go this way, because you still can't cross that x is equal to 1. So that is my horizontal my vertical asymptote.
Wait, so it's not one graph?
Well, it is one graph. The graph of this is the green one.
Oh, okay. That's what
So you could erase everything else. I was just showing you one transformation at a time. So you could do it.
On the y-axis would have been if there was negative x.
Yeah, if the x was negative. So your graph here is the green one. This. All right, so next, here we have log base 4. So I know this graph is going to be the inverse of my 4 to the power of x graph. So 4 to the power of x would be 1/4, 1 and 4, so here. So that's this one. Next, I'm going to graph log base 4 of x. This is just my base graph that I'm just going to flip all of these points. So instead of being -1, 1/4, I'm going to be 1/4, -1. So down here at 1, 0, and then at 4, 1. So here. So I just flipped my exponential graph there. So it's my log base 4 of x. And now I'm going to apply my transformation to it. So I'm going to actually do this graph that it told me to. So what does that -5 do to my graph?
horizontal shift to the right.
It is a horizontal shift to the right 5. So I'm moving all of my points for the blue one to the right 5. So I'm going to go 1, 2, 3, 4, 5. Right there, there, and there. Then just connect your dots. So just be careful. For the blue one, my asymptote was at 0. I'm shifting that vertical asymptote to the right 5. So now my vertical asymptote is at what? How do you write it? Vertical asymptote is x equals 5. So just be careful that you don't cross that vertical asymptote when you're drawing your graph. The blue line was the inverse of the pink one. So the pink one for my 4 to the power of x, the points that I plugged in were -1, 0, and 1. So this would be 1/4, 1, and 4. So then I took my x's and made them my y's, and my y's and made them my x's. So I flipped the points of this here.
So only you have to find the base.
So if I started with log base 4 of x minus 5, how would I know what numbers that I want to plug in here to get my key points? It's harder for us to evaluate logs in our head, but we do know what 4 to the power of -1 is, what 4 to the power of 0, and what 4 to the power of 1 is. For a log graph, this basic log graph here, log base 4 of x, we would want to plug in 1/4, 1, and 4. So it's just kind of easier for us to just go here and just like, it's an additional step to find the inverse, but it's easier for us to graph it. What is my domain of the green graph?
5, infinity.
Awesome, 5, infinity. So your domain starts, the basic graph would be 0 to infinity, but since we shifted it 5, our domain also shifts 5 to the right, so 5 to infinity. What's our range?
Oh, really big one?
The green one,
Negative
All real
infinity.
numbers.
all real numbers.
Oh.
So negative infinity, positive infinity. What is my x-intercept?
5 or 6.
6, 0. I cross the x-axis at this point here, which is 6, 0.
5, 0. No, not 5,
And then my vertical asymptote I found here, which was x is equal to 5. Next, we have the natural logs. So log base e, which we learned about e yesterday, which is just some button in our calculator, is the same thing as ln. So if I had log base e of 10, that is the same as saying the ln of 10. So log base e is just our natural log. Ln of 10 would be the same thing as log base e of 10. So you can change ln to be log base e, or change log base e to be ln. Okay, so luckily for us, we have a button in our calculator that is ln. So here we would just put it into our calculator. 2 times the ln of 12.5. So first I would find the ln of 12.5, then just multiply it by 2.
$5.051.
5.051.
That is not what I got.
So Michael, on your calculator, remember you have to do it backwards. So click 12.5, then the ln, and then multiply that times 2.
Oh, okay.
Yeah, I think that's, Paloma, yours might be the same. Just make sure you know how to use your calculator. So sometimes you have to put it in backwards. Sometimes you don't. All right, for the next one, we're using our properties of natural logarithms to rewrite the expression. So it doesn't give us a slide with properties of logarithms, but one thing is that if we have log base e of e, we know log base e is what? Ln. So log base e of e, what happens here? It cancels. So that's the same thing as saying ln of e, it cancels. Ln of e is just 1. Also, if you had e to the power of ln, this is just 1. So it would cancel here as well. So for a, we have -5 times ln of e. What is the ln of e? 1. And -5 times 1? -5. So our answer is just -5. For b, we have e to the power of ln of 7. It's just 7. So e to the power of ln cancels, and we're just left with 7. So here we have the ln graph. ln is the same thing as our log. It's log base e of x minus 3. If I were to graph first e to the power of x, I would get, let's say I plugged in -1, 0, and 1, just like I did before. I would get -1, 0.37. You can put that in your calculator. It would also just be 1 over e, which was 1 over 2 point something. So it's 0.37, so about here. If I plugged in 0, it's e to the power of 0, 1. So 0 up 1. And if I plugged in 1, 2.7 up here. So that's my e to the power of x graph. Well, now I'm going to do my log base e graph, so log base e of x. So I'm just flipping my x and y's. So the x's become y's, the y's become x's. So I flip all of my points. This one would be down here, right here, and go to the right 2.7 and up 1 here. So this is my log base e of x graph. Now I'm going to apply my transformation to it. So what does this minus 3 do to it? 3 to the right. So I'm moving to the right 3. So I take each one of my points, move it to the right 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So my vertical asymptote, I would find it the same way that I found in the log function. So set whatever's in your parentheses equal to 0. So x minus 3 equals 0. X is equal to 3. So that is my vertical asymptote. So our graph shifted to the right 3. So instead of my vertical asymptote being at 0, I just shifted it to the right 3. Because my whole graph shifted to the right 3, so the asymptote shifted with it. So the green one is this, the pink one is this, and the blue one is the one we're actually graphing. So if once you graph the green and the pink, erase it. You don't need it. So the blue one is our actual graph. We just use the green and the pink to help us get there. Now what's the domain of our blue graph? 3 to infinity. Awesome. What's my range? All real numbers. And what's my x-intercept? 4. So it would be 4, 0. Do I cross the y-axis? No, so there's no y-intercept. And do I have a horizontal asymptote?